Hello, and welcome back to my coding channel here. Today we're going to be doing another little thing in Raylib, hopefully a little more interesting and a little more reasonably paced than my Papers, Please demo. I'm going to be doing something that's actually considered a game. It's a game that you've all probably played, which is, of course, Minesweeper, as you see from the title. The reason I wanted to do this was because I was watching a channel that I really enjoy, which is The Coding Train by Daniel Schiffman. And when I was in high school and learning my first little bit of code, I learned a fair amount of it from him. So I quite enjoyed his stuff. And lately, while I'm working, I'll have it open on my second monitor. And watching him do Minesweeper, I just thought it was funny because I guess the extra pressure of doing it live and I don't really know. For whatever reason, it was just very difficult for him to do it. And I just thought it'd be fun to give it a shot myself and see if it's really fair to be so critical. So today we're going to be building Minesweeper, and it's not going to be pretty or even really that good or fun probably, but I'm hoping it will give us a chance to play around with some Raylib specific stuff, and I guess just kind of practice doing some more C programming. So to get started, I've got a really simple sample project here that I always use whenever I'm making a Raylib project. So if I just go ahead and compile and run it, we'll see it's just a window. It says example window. So it's very similar to what you get from the Raylib like minimal window example that you can kind of use to test your compiler settings and everything. I've got some extra includes at the top though. I'm going to include RayMath from the beginning as well as standard library and time because I know I'm going to end up using rand. So I've seeded the random with just the current time. I've got a few things here. We're going to end up adding a bunch of variables to this, and I'm going to try and keep it in one file because I'll have a video coming out sometime after this video that explains how you can use multiple files to break up your programs a little better. But for now, we're just going to keep it all in one file. So to get started, I'm just going to define some constants here that are going to help us with putting everything together. So the window is really, for now, it's just going to be the game. So Minesweeper is a grid, which means it has a number of rows and a number of columns, which are each going to be 10 for now. And we have the screen width and screen height. I'm going to set these to 400. And I'm also going to mark them as const. And then we're also going to have the constant, which is a cell width, which is just going to be screen width divided by the number of columns. And similarly, we want the cell height, which is the same thing, but with the screen height and the number of rows. If you want the cells to be the same size, then the ratio between columns and rows and the ratio between the screen width and height will need to match. So whatever the number of columns is, acts as kind of the width. So if I was to double this, I'd have to double this. I wouldn't have to double rows because we're using the width and height separately. And I don't know that that's actually going to come in handy later, but I'm going to try and build most of this fairly general. So we've got these. Just quickly, I'm going to, as to sort of demonstrate the logic that we're going to use to build a grid by using nested for loops, I'm just going to draw the grid, but not using the cell struct that we're going to build in a second, just as to sort of show the coordinate system. So with a for loop, I'm going to do the standard I0, and then the upper bound of that is the number of columns because I want to iterate. I'm going to use I as like my X value. And then in here, we're going to have another for loop, which is going to use J, and it's going to use rows. So now within this nested for loop, we can write some code. I'm going to use the draw rectangle lines method from Raylib. So it takes a position X, which is going to be I times cell width, a position Y, which is going to be J times cell height. And then we need the width and height, so cell width and cell height. And then lastly, a color. So draw rectangle lines is just going to draw like a hollow rectangle, basically. So we're going to draw columns number across, horizontally, and then rows number vertically. And that's going to just end up making a grid. So we'll run this, see if it works. And there we go. We've got a grid. So now that we have a grid, it's like we've already done a huge part of Minesweeper, but we haven't because all I've done is draw some lines. So if I wanted to have logic to have cells that have their own state, then I'm going to need to use a struct to sort of bind all that data together. So it's going to be a lot easier for me to achieve that if I actually create a struct. And instead of just using draw rectangle lines, I'll actually use this logic to draw some kind of struct that is going to hold on to this data. So the way I'll specify that, I'll have a struct cell. And I'm going to actually type def this so that we don't have to write struct every time. So for just as a sort of initial setup, I'm going to give each cell an I and a j, which is going to represent their index. And with this, I can basically take this for loop, move it into this like setup area. This is kind of where you would put your setup between init window and the while loop starting. And instead of drawing rectangle lines, I can actually say, oh, and you know what? Let's actually have a place to put all these. I'm going to make a two-dimensional array. So that's fine. I can use, you can't put variables for an array, but if it's a const, then it'll work. So if I was to put screen width, then we'll get a little warning here that says the variable length array is folded to a constant array. So you can see that my const value has become that. Whereas if I was to put like a regular variable, like if this wasn't const, I imagine the compiler is going to give us an error. Yeah, because it's a variable length array. So the size of the array isn't known to the compiler at compile time. That's an important, how arrays are worked. Arrays are static and see they're part of the program's stack memory from the beginning. So the compiler goes through and kind of figures out a worst case scenario. At least that's my understanding. Could be totally wrong. But yeah, we need to make sure these are actual values and not variables. So I'm going to create a grid two-dimensional array. So it's so this is like the width and this is like the height kind of thing. So each entry in the array represents one column, and then each of those columns contains rows, many entries. So as long as I always access it with the x and then the y value, we're good to go. And when I say x and y, I really mean I and j, because x and y I'm going to treat as like the in-world position, and then I and j are just the indices. So now instead of drawing all these rectangles, we're going to grid at I and j. We're going to create a new cell. I should put it like this, where the the I value is equal to I, and the j value is equal to j. So that's pretty straightforward. And this is a C99, I believe, named members, or whatever it's called. Named member initialization, I think is what it's called. I just like to do this because it's explicit, since there's no compiler checking against what we put in these. So it's helpful to me to do these so that I can see that I'm doing all of them. And typically when there's multiple values, I like to expand it like that. So there we go. So you can see IJ, IJ. So it's like easy to read. So we're going to go through this loop once to create all of the cells, and then every frame we're going to take this logic, and I'm actually going to move it into a new method here. So I guess the function, I should say. So I'll write cell first, so that any function that pertains to a cell starts with the word cell, so that if I ever need to find a method or function that applies to cell, I can start by writing cell. And cell draw needs to take a cell as a parameter. And down here, I can define this to be cell, and we're going to do exactly the logic that's here, except instead of it just being cell, it's cell, or instead of just being I, it's cell.I and cell.j. The rest of these are constants, right? Cell width, cell height are all constants, so we don't have to do much else there. So now instead of calling all that logic, I can just say cell draw, and I can say grid at I and j. Okay, so hopefully when I build again, we're going to have still the same image. Yep, looks the same. So again, it doesn't seem like anything has changed, but now each of these cells have their own data. So I could do, I could just kind of demonstrate. And visually, we're going to be missing, I think it's the fourth column. Yeah. So next, we want to add some state to the cells. So a cell is going to have a Boolean that determines whether or not it contains a mine. It's also going to have a bool to determine whether or not it's been revealed. And I think that should be okay for now. So we're going to add some functionality. So when we click the mouse button, is mouse button pressed? Stick that in an if statement. So if the mouse button left is pressed, then we're going to execute this logic. This is only on the frame that it's first pressed, and it's not going to be true every frame that it's held. So the user will have to click on each cell independently. They can't just hold the left mouse and throw their cursor all over the place. We're going to get the position of the mouse, and I'm going to use the position's x value and divide it by the width of a cell to get an index I. I'm going to do the exact same thing for the letter J with the y and height. So the reason that we're doing this, every single one of these squares is cell width wide, right? That's kind of intuitive, I guess. So if I was to have the mouse cursor at this position right here, and I was to divide it now by cell width, I'd get 1, because it's 1 unit over. And if I was to move it over to here, I would get 2. This one, for example, it's going to be between 0 and 1. When it's in here, it's between 1 and 2. When it's in here, it's between 2 and 3. But it's only going to be 1 once I cross the threshold, right? So if I divide my position now by the width, I'm going to get 0. So then we're going to use the fact that integer division is automatically truncating towards 0, meaning when you divide a number by an integer, you're going to get an integer back, and that integer is going to be, if it has to round, it's not going to always round the way we're taught in school, where if it's more than 0.5, it's going to go up. It's always going to round down, and we can actually use that to our advantage here to easily get the indexes we need. So keeping that in mind, I'm going to use this index I and index j to determine which square we've clicked on. So now we need to just do some quick protection logic here. So I'm actually going to have a method that says, or a function that says index is valid. I'm going to pass in index I, index j, and we're going to write this method. I keep saying method. It's a function in C. So this is a really simple thing, and it shouldn't be void, actually. It should be bool. So the index is valid if I is greater than or equal to 0, and I is strictly less than columns, and j is greater than or equal to 0, and j is strictly less than rows. So if all of that is true, we've got ourselves a valid index. So we're just going to return this. Now, obviously, this isn't a super complicated expression, but to write index is valid and put in 2 things will be shorter than this. And more importantly, it's less error prone if I don't have to keep writing this out. If I have the definition one time, it's going to save us a lot of trouble. So if that index is valid, this just kind of protects me from accidentally accessing an array element that doesn't exist. I can say the grid at that object. I'm sorry, I need to write index I and index j. So what I'm going to do is just set this one to revealed equals true. So the thing is, when this happens, I want to do a bunch of extra logic. So instead of having that cell reveal, pass in the cell, but we're going to pass in a pointer to the cell. Does that make sense? Nah. Let's just go ahead and give the ints again. I think that's been working okay so far. So this logic right here, cell and reveal, because I want to, at the grid, I want to access this thing. And then basically, if this value right here if this contains a mine, then this is lose. And then in this case, we're going to play a sound. I'm just going to write play sound for now. That's going to be kind of a polished step that we'll get to after. So currently when we draw the cell, we don't use the value of whether or not it's revealed at all. So we're going to quickly add a bit of a case here. So here I've broken it up into a few different cases. So if the cell is revealed, then we have 2 cases. If it contains a mine and if it doesn't. And then I've left the draw rectangle lines down here because I want to always have that grid. I think that's a valuable thing to have. But in the case that the thing has been revealed, we want to use the regular draw rectangle method with all the same parameters, except I'm going to give it a light gray, just to show that the state has changed when we click it. And if it contains a mine temporarily, I'm going to do the exact same thing, except I'm going to change it to red. So let's go ahead and run this. And we've done a lot of changes here, so there could be an error or unexpected something. No, looks pretty good. So when I click, they turn gray. Obviously, none of them contain a mine because we haven't added that logic. But I'm just going to make it so that the first 5, or the first in every single row is going to contain a mine, and then that way we can see that logic working. I have to remember to actually set these values explicitly. They will default to false, as that is the default value in C, but I'm not sure. You know, I don't feel confident in that. I think it's a bad practice to leave something uninitialized like that. So we're going to explicitly set them to false. Looks good. Okay. So now we need to try and actually place the mines into the level, because right now we just have a bunch of tiles. There's no mines. Which means you instantly win. So what we're going to do is a little bit perhaps strange. It's definitely not the most efficient algorithm, simply because an efficient algorithm when it comes to random is kind of a button topic, and there's a lot of ways to do it, but we're going for simple here. So what we're going to do is have an int, which is mines to place, and I'm going to set this to being 10% of the total number of tiles. So rows times columns times 0.1f. And obviously this makes it into a float. And then we would need to have it become an int. It's going to happen implicitly, but I'd like to explicitly cast it here just as good practice. Generally speaking, when you're going to cast, it's good to make it explicit. Some compilers and some settings actually require that too, which is kind of fun. So we have a certain number of mines we have to place, and then while that number is greater than 0, we're going to go over the entire list, picking a random index, and if it doesn't have a mine, we're going to put a mine in it, and then we're going to move on. So the index, because I can do 2 here, so I is going to be rand mod columns, and j is going to be rand mod rows. Now, what we're going to say is if grid at ij doesn't contain a mine, then we're going to set that grid value for the mine to true, and the mines to place is going to be reduced by 1. So we're not going to reduce it in every iteration of the loop. We're only going to do it when we successfully place a mine. Now, the reason this isn't a super good algorithm to do random generation, and you know, like I said, sometimes it matters, and in this case, it really doesn't, because this is supposed to be kind of a quick video. The best way to do this is to figure out what the indices are ahead of time by maybe grabbing, like, by just taking like a full list of them maybe and shuffling them and then pulling a finite number. Because since I'm relying on randomness here, it's possible technically that I could pick the same number repeatedly and get stuck, or I could pick a small handful of tiles and populate them, and then finding that last tile, we could get extremely unlucky and keep choosing the same handful of tiles for a very long time, or if you want to be dramatic, forever. But I will at some point show some shuffling algorithms because it's going to be helpful when working on games when we want randomness, but we want unique randomness. Now I'm going to set all the revealed values to true so we can check the distribution and see if we're getting 10 or maybe something's going wrong. Looks like I'm getting 10. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 10. Yeah, I think it's working just fine. It'd be strange if it wasn't. If anything, it would be an off by 1, and it would be happening in all of them. So we can set the revealed back to false, and we can run it and see what the game will really look like, where all the tiles need to be revealed, and we can click to clear them. But if we hit a mine, that's too bad. Now, if you've ever played Minesweeper, you'll know this is ridiculous because I can keep playing after I've hit a mine. So there needs to be a game state. And before we even get to that, there should be a way to know where the mines are, because right now it's random and it'd be very difficult to win. But if you want, you followed along from now, you could copy all this code and see if you can win without ever tripping a mine. But I think that would be very difficult. So now we're going to make it so that the tiles actually tell us information about the nearest mine. So in Minesweeper, we get a number that tells us how many of the neighboring tiles are mines. And when we say neighboring tiles, we mean, so for this tile here, all of these tiles that I've selected, that's a cool pattern. All of these neighboring tiles here are neighbors to the center one here. So here's one, then these 4 corners, and these 4 edges. So this is, one set. So what we're going to do, again, it's not the most efficient way to do this kind of thing, but we're going to go through each tile, and each tile that isn't a mine, we're going to count how many mines are around it. So for this tile, the number would be 0. For all of these, let me clear these out like this. So for these tiles here, it's going to be 1. But for these 2, it's going to be the number 2. And the way that we'll do that is, well, for this tile right here, I'm going to look up and left, then up and right, then left, then at myself, but I'm not going to count myself, then to the right, then down to the left, down, and down to the right. So the way we do that is we have -1, -1, -1, 0, -1 plus 1, and then we have, -1, 0, 0, 0, +1, 0. So it's another nested for loop. You won't believe it. So after we have created all the cells and placed all the mines, now we're going to go through each cell and we're going to actually store this value in here. Let's store a value of nearby mines. And in here, like I said, we're going to do another nested for loop. For each tile. For each cell, I should say. So we're going to set the nearby mines equal to cell count mines, and we're going to pass in ij. And we're only going to do this if that grid does not contain a mine. So if it does not contain a mine, we will do this math. If it does, we're going to actually just set it to -1. Well, you know what? I won't set it to -1 here. I'm going to have it set to -1 by default. And then we're only going to give it a value if it doesn't contain a mine. Now, this cell count mines doesn't exist. So what do? Create a function prototype. So, for those of you at home who are paying attention, we have a loop for every column, then a loop for every row, and then for each of these, we're going to have 8 things that we have to do. And it just, if that seems like it's getting inefficient, it is. But the good news is this is the setup for the game. We're only doing this at the beginning. So like I said, games have loading screens for a reason. You can always have a little sign that says it's loading, or realistically it'll happen instantly, so we don't need to do this because computers are so quick. But if you're building this for a calculator, then you might want to get a little more clever with how the data is laid out. So to count the nearby mines, again, we need, like I said before, I'm going to use 2 loops, but it's not going to be the way you think. It's going to be from -1 to including 1. And I'm going to do the exact same thing on the inside, except we're going to use j. And I guess I can't really use these because they already exist. So we're going to say I don't know. I guess I'll use capitals. I don't recommend you name your variables like this, to be perfectly honest. Oh, I guess we can call it off. Although it seems like it's kind of a rude... It seems like I'm trying to say a rude thing, but I'm really not. I'm meaning offset when I say off. So for each of these values, all we need to do, we're going to have an int, which is I plus I off. And what we need to do is have an if statement. So if index is valid, I plus I off, j plus j off. So only if the index is valid do we want to do this. And what we want to do is we're going to have some kind of count value up here, which we start at 0. We increment once for every time that we find a valid index. Oh, you know what? And I've gone a little too far. I'm going too quick here. It's not just if the index is valid, because that's going to be 8 for almost every tile. We want to see if grid at I plus I off, j plus j off. See, it just sounds rude. If that contains a mine, then we increase the count. And the other thing, we want to have one more exit case, which is if I equals 0 and j equals 0, then we want to continue. And you know what? To reduce how much nesting there is here, I'm going to say if this index is invalid, that we're going to continue. And I'm going to pull this down here because I just think it was getting too tall. You know, I'd rather have it be wide. Or I guess you could say deep because it was coming too far, you know, left to right. So basically, we have these things that we go for. So we start from -1, up to 1, 1. If it's 0, 0, that means we're counting ourselves, which, you know, we don't have to do, but technically it would be 0 anyway because we know that we don't contain a mine because we don't run this for cells that contain a mine. We also, if the index is invalid, we're going to just continue, meaning we'll go on to the next iteration of the loop. And then if grid at ij contains mine, then we'll increase that count value. And at the very end of all these loops, we're going to return it. So now we should be able to assign a value of the nearby mines to every single tile or cell. I keep calling it tile, but it's cell. So all that's left to do on the numbers side of things is make it so that when we have revealed a cell and it doesn't contain a mine, we should draw the number of nearby cells. And that's actually really easy. We can use draw text and text format to take an integer value and place it in a string. So that integer value is going to be cell.nearbyMines. The position is going to be kind of the same here as this stuff, except I'm going to add a little something to it. So I'm going to move it in by 6 pixels and move it down by 4 pixels. Let's say. The font size, I'm going to make it the cell height, but I'm going to remove 8 pixels, 4 for the top, 4 for the bottom. And then I'm just going to write the text in dark gray. So it's not going to look too, it's not going to be black, so it's not going to look, I don't know, I think it'll look cool. We'll see. This kind of stuff of knowing to do, you know, plus this, minus that, that just comes with time. You'll figure that kind of stuff out over time. Okay, there's no tiles here. There's 2 tiles near these guys. Oh, I know exactly where they are. I can avoid them. How amazing. Oh. Okay. Okay, well, we're getting somewhere. So if it's 0, we shouldn't draw it. And it looks like actually drawing those 6 is not enough. I'm going to go up to 12 pixels. And we're going to add an if statement here. If this number is greater than 0, that's the only time that we draw that. Okay, well, it looks like the numbers are getting the right values because the ones are all around. I know there's a mine right here. Boom. So it looks like that's definitely working. I think it would be nice to place a flag on a mine on a tile, so that we can show that we know that there's a mine there. So to add a flag, I'm going to need yet another thing here. So we have revealed, but then we also have flagged. Technically, I could combine these into an enum state of some kind, but I think just for simplicity, we'll keep them as separate bools. When we try to reveal a cell, we're going to add a case here if that cell is flagged, we're just going to return. We're not going to actually do anything. In the draw case, if it contains a mine, else if, oh sorry, this is revealed. In the else case to revealed, we're going to see if it's flagged. And I don't have like a flag thing that I can use here. I'll just need to see if I can grab a flag sprite. Okay, I have located a flag. I need to actually load this in Raylib. Let me leave a comment here so I can find it after. So to have a flag, to have a texture, if you're working with textures, and I'm going to have a full video about textures later, it's always important that you remember to do it after init window. I've gotten stuck on that many times when I'm trying to figure out why my program suddenly wasn't working anymore. And it was because I had moved my init method before the init window because I thought, oh, maybe I should do some of the loading before the window pops up. Maybe that would be interesting. I wanted to see what it would look like. And I had done that without testing, so I didn't realize that it would break something. So make sure you always do your load textures, load sounds, anything like that after. And that's the other thing too. If you need to load sounds, you need to remember to init audio device so that you have a place to actually load that audio to. So I have the sprite. To draw a sprite, also, there's a bit of extra work you have to do. So you need a destination and a source rectangle. So the source rectangle is easy because I can use 0, 0, and then I can use flag sprite width, flag sprite height. And that'll just get the whole image. But to use a destination rectangle, I need the position where I want the image to be, which is easy because I have that here. And I need the width, which is easy because I have it right here. So again, because of the way we've set up the data, it's actually very easy for us to create a destination rectangle. If my position described the center of something, I'd have to change quite a bit of stuff that way. So that's actually fine. We're also going to need a vector2 called an origin, but I can just make this 0, 0 because I don't like I said, we're drawing from the corner, so we can use 0, 0 as an origin. So we need to use draw texture. I wonder if I can get away with, let's just go pro. Let's make this easy. So we want to draw, what's texture rec? Hang on. No, I want to use pro because I want to be able to scale it down because I know this image is definitely bigger than the flag image, or than the cell thing. So we're going to use the flag sprite here. We're going to use source, dest, origin, 0.0 for the rotation, and white for the color. The flag is not white, but it's the tint, and I want to use the full color of the image, so we can use flag. In fact, actually, let's go ahead and fade this by 0.3f just to make it look a little more, just to make it look like it's more a part of the thing. Maybe that'll look better. Let's see. I just realized I have no way to flag a tile. We need to actually add that logic. So up here, when we check if the mouse button left is pressed, we can add an else if case for if the right mouse button is pressed. So I'm going to use this exact same logic here to get the position. And I'm going to do the exact same thing if the index is valid, except instead of saying cell reveal, we're going to have a method called cell flag. Just copying the prototype. And I'm going to do exactly the same stuff. So if, actually I can do this a little differently. So it doesn't actually matter whether or not the cell is flagged. What matters is whether it's revealed. And then here we can set flagged to whatever it wasn't already, because with cell flag we can actually enable or disable a flag, and doing that will actually do nothing. No sound effect or anything like that. Okay, let's see. So if I right click, we can place a flag. Look at that. And if I click on a flag, I can't actually clear that tile. Okay, well, that was unlucky. Oh, that's even worse. Okay, let's try over here. So 1, 1. So I know this one's safe right here. I'm going to guess that this one is safe. Yes. Okay, I think there's a mine here. Yes. And I think there's one here. Okay. See, I've never been very good at Minesweeper, so when I get to this part, well, I know that's a mine. Usually you can't play once, you lose once. When I get to this point up here, I don't know what to do, right? So I know that it can't be one of these. Oh. I guess I am good at Minesweeper. Okay. I think that fade is a little too harsh, so I'm going to tone that down just a little bit. Put it at about 50% transparency. When you click on an empty spot in Minesweeper, it's supposed to have like a flood fill. So when I click on this one, we should really get all of the other empty tiles near it should all quickly reveal, and these other numbers here. So that should happen. And then coming this way. So that should happen, right? When we click. So what I just did was actually I kind of spelled out the algorithm there for us. So what we really want to do is when we have a tile that is revealed that is empty, I want to go to each of these neighbors and reveal them. And for each of those neighbors, if that neighbor was empty, so this one's empty, I want to do all of these. And then so I want to go to this one, you know, this one here, it's still missing a neighbor, and I'll go to that one and I'll do a check of its and so on. So I'm kind of cheesing it a little bit, but we're going to go ahead and set that up now. Oh, by the way, it's not great that I have all of this logic just sitting here. So I'm actually going to create a void, which is just going to be grid init. And this can be a void method because I'm just going to copy and paste all this logic. The grid is actually a global value here. See cell grid, it's actually global. So everybody can access it, all the methods. So there's nothing in this nothing that lives in this grid init logic that isn't accessible from the entire program. So I can move this logic in here, compile, and we'll see that the game is working just fine. Whoa, it's not. What happened here? I'm going to use the debugger here, which is another really awesome thing that, oh, it's never called. See, the debugger is really good. I forgot to actually call the grid init method. Hey, listen, it happens. Okay, there we go. Now the game is working just fine, as we can see. So we want to make it so that when we click on a tile, if that has no neighbors, we're going to do kind of a flood clear thing. So in the same way, we've got these two methods up here. That's why I put cell reveal in a method, because in the case that doesn't contain logic, we're going to play sound, and then we want to do a little thing here. So if grid ij nearby mines equals 0, right? This is kind of a special case. Then we're going to say flood fill from, let's say grid flood clear from, and we'll pass in I and j. So what flood clear from is going to have to do, and we're going to want to go up here, of course, write a void method. So what we're going to have to do with this is we're going to say for, and we're going to do the exact same thing we did before with the -1 to 1. So this double loop right here, I'm going to copy this into here. And what we're going to do is if I and j is 0, we're going to continue. If that index is invalid, we're going to continue. And then in this case here, instead of saying if it contains mine, if it hasn't been revealed, then we're going to say cell reveal ij. And keep in mind that in revealing that cell, it's going to call this logic. It's going to go through here. And if it has no nearby mines, it's going to call this again on that guy. And it's going to recursively go through, and hopefully it's going to flood clear the grid. So let's go ahead and run, and let's see if we can't get some luck with that. Okay. we got an exception, and it's a segmentation fault. So let's see what kind of issue we're having here. Oh, this is a terribly upsetting mistake. Okay, so here I'm checking if I and 0 are equal in order for us to continue. But we need to actually check this offset value if it's 0, because we don't want to check the tile itself. But what's happening is we're always checking the tile itself and then giving up, I guess. I'm not really sure. I mean, I'm acting like that's going to be the solution. I know that that was definitely a problem. Oh, and I just spotted the real problem right here. We're not using the offset in this part. So it was kind of the problem, just in a different spot. But I mean, really, that's upsetting. Whoa. This game is working. Let's play Minesweeper. Wait a second. Okay. I don't understand what just happened. I just won in one click. I think the only piece that I had to clear manually was this one right here. Okay, well that was a really insane fluke. Let's try again. So here's the trouble, right? Now this one right here, which of these two is a valid tile? If anybody who watches this is like a Minesweeper pro and you know how to solve this kind of thing, then you should definitely leave it in the comments, because to me this is random. Okay, so I win. Like that, you know, it just feels like that was random chance. Like that's a bomb. It could have been this one. Like I don't know if there's like I really don't know. I don't know if there's a way you're supposed to fix that. But anyway, for the most part, it looks like everything's working. The flood fill seems to be working. This tile right here doesn't have a number, so I wonder if it's an edge case of the index being 0, 0. Yeah, and look at this. I had the exact same problem here. So that must have been how I got that error, because I copy pasted this logic, but it's actually the offsets that we want to check there. So that means that at the cell 0, 0, the number wasn't going to compute. And this time, of course, it's a number that it actually is blank. But if we go to this one, that was blank. Oh my God, this is hilarious. Okay, there we go. So we can see there's an example with a number. So that's good. So to add some basic game state is actually fairly simple. Every time, well, let's go ahead and have an enum here. So we have an enum which can be playing, lose, or win. So this is just going to help us control what we should display and what kind of interactivity the user can have. So when the mouse button is pressed and we do this cell reveal thing, we want to make sure, oh, and I should actually create a game state variable called state and set it to playing in the beginning. So when we do this, we want to make sure that state equals playing before we attempt to clear a tile or to place a flag. In this thing here, we draw the whole grid, but if the state is lose, then we're going to draw a rectangle at 0, 0, which is screen width, screen height, and I'm going to draw it in white, but I'm going to fade it to 80%. And then, oops, I'm going to draw some text. I've declared some constant characters in this loop. I'm going to move them up here. So we're going to write you lose. I'm going to put it at screen width 2, screen height 2. This is another thing that I'm definitely going to have a video out later about. But in order to actually put something in the center of where we're saying we want to draw, instead of just putting it at screen width by 2, we want to reduce it by measure text, which means we have to pass in ulose again and the font size, which I've declared right here. And then I would divide that by 2. So I'm putting it in the middle of the screen, and then I'm moving it left by half of how wide it is so that the text will appear to be in the center. And to make it vertically in the center, I need to add 10, or remove 10 here, which is half of the font size, because font size in Raylib is actually going to be the height of the glyphs. So if we do this, then when we've lost, we're going to cover the screen with a little message, and I'm going to do the exact same thing for win, except it's going to be you win, and I don't have to change anything else, except I need to actually define a you win. It's going to be you win, and then I should probably include these press R to restart messages as well somewhere. So something this doesn't have is the game time. That's something we'll add after. So we have this functionality, press R to restart, but if they press R, the game's not going to restart. So we should probably add that as well. So if is key pressed, key R, I'm going to say reset game, and you better believe that's going to be another void method. Jump to the end. So in reset game, we're going to do everything we do at the beginning of the game, which is just to init the grid, actually. But we're also going to set the state to playing. So I'm going to find out where I'm setting this originally, get rid of that. And instead of calling grid init, I'm going to call reset game. And actually, I'm going to rename this to game init, just to be more clear. It's better than just reset game. So game init has to grid init, and then it sets the state. And I really do think that's going to be all there is to it. So we need to add the lose logic. So here I say lose, so we're going to set state to lose. And when we reveal a tile, when we reveal a mine, I'm going to say tiles revealed ++, and then I'm going to say if tiles revealed is greater than goal, or we'll say rows times columns minus mines present. Right, so I'm going to have to add a bunch of new things here, but this is when we will say state equals win. So tiles revealed and mines present. Let's add these. So mines present, when we say game in it and we say grid in it, and I say mines to place, I'm going to actually cut this and set it equal to mines present, and we're going to set mines present to this value. So mines present is the total, and then mines to place is actually used by the generation. So mines present is what I'm going to use to say, you know, is there enough left? So when we do this check here, so this is 100, this is 10, 100 minus 10. So if the tiles revealed is equal to this amount, then the state has entered the win state, and we're going to see the you win screen. So let's give it a shot. I mean, we've done a lot here. Let's see if any of this is working. Maybe this will be the secret sauce. Oh yeah, it was. I win. Look at that. I can press R to play again. I press R, I'm able to play again. And that's the truth about Minesweeper right there. On one attempt, I got it in my first try. On the next attempt, I lose immediately. That's Minesweeper, baby. That's what we're here for. Okay. These, I can get rid of this and this. And I think I've won. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh. Okay, well, that was dumb. I knew that was a mine. Oh, what? Oh, my. Okay, well, I know I didn't win here, so that's alarming. So this tells us a lot. This tells us that tiles revealed is going up too far. It's getting to a value that is much too high. So what we can do is we can breakpoint this and run the program again. So if I look at tiles revealed, the number's 91, which is impossible because there's only 90 tiles we can click without losing. So I'm gonna hit continue, and we're gonna see I clicked on one tile and it says I win. And here's the interesting part. Watch this. If I press R, I win again. You notice something? I win instantly. So, okay. So, potentially part of this comes down to the tiles revealed is still set to whatever the number was in the previous run. I don't think that was the problem. But it did seem like it was only an issue with subsequent runs. Anyway, I'm going to keep playing and I'll let you know. Okay, so this should win. And we win. Let's hit play. Let's hit R. Let's play again. No. Okay. That was intense. No, why did I do that? I didn't even think. The way this has been built, it should not be very difficult for me to bring it up to 600 by 600 and make it 30 by 30. I should be able to just change those two numbers and we'll see the change in the code. Now this is interesting. No, I wasn't thinking. To be clear, there is a better way to there is a better way to do that. So if I'm doing that, it should be 20. It should be 15 by 15, and they should be the same size. There is a better way to zoom in your game than that, and that's the kind of thing that I'd be interested to explore in future videos, working with the camera and sort of dealing with the zoom and things like that. You know, there's some interesting questions that come up, and a lot of games end up needing something like that. So it's definitely a valuable thing to explore. For the purposes of this video, I can't help but feel as though we're done. You know, we're done here. I don't need to keep playing this. So I feel like there was something else I said I wanted to implement, and I don't remember. Oh, right. Of course. It's how long they've been playing. So that's a big one. So when we... That's actually really important that we get that right. So when we game init, let's have a float called time game started, and let's have a float called time game ended. Now when we init the game, we're going to say time game started is equal to get time. Get time is going to tell us the elapsed time in seconds since we called init window. So we're going to say get time, and that's going to give us the current time when the video is starting, and then, or when the game is starting, sorry, and then when we lose, whether it's we lose or we win, let's see here. So when state equals lose, we want to say time game ended is equal to get time. And when we say state equals win, which is down here, we want to do the same logic. So when we show state equals win. So when we show the time, or when we say you lose or you win or whatever it is, time played percent d minutes, comma, percent d seconds. And where are we going to get these? And in this case, we're going to make sure that we integer cast this as well. Okay. Well, that wasn't much of a round. I played for 2 seconds. See, it's stuff like that that makes me think that maybe when I say, like, I'm like, oh, I have to guess here. Then oh, I wasn't paying attention. And I did it for exactly 1 minute. See, when you get a number like that, it makes you think that the calculation doesn't work, but I assure you that it does. Okay, if there's 2 here and there's 2 here, they're sharing the same 1. Each of these needs 2 and each of these needs 1. So 1, it could be this one or this one. According to this 2, it could be either of those. According to this 2... No! Okay, whatever. I'm happy. I'm happy with what we come up with here. It seems like it's a lot of fun. Obviously, I'm still playing it. But that's no credit to me. That's Minesweeper. Minesweeper is just kind of an interesting, fun game. I'm going to leave the source in a grid arrangement of 15 by 15, but there's nothing stopping you from changing the screen width, changing the screen height. You could even make the window resizable in Raylib and have it so that every time it's resized, we update these values. Granted, they are const, so it's going to shake up a lot of the code. You have to change a lot of things to being evaluated every frame, but if being able to resize the game is really important to you, you can do something like that. Something else you can do is, right now the grid size is based on screen width and height. You could define a play area width and height and replace everywhere we're saying screen width and height with play area width and height, and then you could sort of inset everything, and you could fit some room for some HUD elements on the top, along the sides, and on the bottom to make it seem like it's a game that has more of a menu. In this case, in what we've built here today, it's really just the game. There's no other, there's no padding, there's no menu elements. Everything's simple events. You know, there's only 3 input styles we have, which is button pressed, and key pressed. So it's a very simple setup, but to me that is sort of what makes it like a really good, fun little project. So, you know, this is the kind of thing where if you're like, okay, I've seen Raylib, you know, I understand how you can make it draw boxes, but how could you make it into a game? Well, obviously, this isn't the most elaborate game in the world, right? It's the kind of thing they gave to every Windows owner for free. So obviously, it's not a super elaborate game. But it might help you with beginning to understand how you can embed your game logic into something like Raylib with the use of all of these different functions and everything. So the source is going to be on my GitHub, and you can feel free to check it out. Feel free to download it and mod it to your heart's content. Another thing you could definitely give it a shot is in these resources, I've included a few sound effects. I don't know what this license is. I'm going to get rid of it. I've included a few sound effects that I really wanted to add when you dig, or like, you know, whenever you clear a tile, and then if you hit a bomb, and then of course if you win. So I would have really liked to implement these. You know, feel free to take a stab at adding sound effects. Use these sound effects. Use your own. It's really easy. They're just in a resources folder. Go nuts. And that's really all there is to it. So thank you so much for watching, and I hope you have a great day.